The triangle PQR on the right is equilateral. That means that the three sides are the same. It also means actually that the three angles are the same. The point G is the centroid. To get the centroid of the triangle, what you do is you take a corner of the triangle and draw a line from that corner to the midpoint of the opposite side. So this side here is opposite this corner. So we get the midpoint, so we bisect this side. So that this distance here equals this distance here. We draw in this line. This line is called a median. We draw another median by drawing a line from another corner to the midpoint of the opposite side of that corner. So this point here is the midpoint of this side. So we bisect this side into two equal bits. The reason I put a double dash here rather than a single dash is because this distance here is not necessarily the same as this distance here. In general, these two distances are not the same. So we have to use a double dash here and a single dash here. By the way, the double dash does not mean that this is twice this, it's just to distinguish them. So we have this second median. And where these two medians cross, we have a point called a centroid. Now we could draw in the third median. We draw a line from this corner here to the midpoint of this side. So we make this distance the same as this distance here. So I put three dashes on the distance from here to distinguish it from all the other distances. When we draw in this third median, we will see that it will pass through the centroid. So the three medians are concurrent. Now that fact is far from obvious, and I will prove it in another video. You can also think of the centroid as the balance point of a triangular shape whose thickness is uniform. That means its thickness doesn't change. So you can imagine trying to balance, say, a piece of cardboard cut out in the shape of a triangle at this point, and that's the most likely point for it to balance on. Well, in practice it's very hard to balance something, but in theory this would be the balance point. So now let's look at the medians of this triangle here. So we draw a line from the point Q to the midpoint of the opposite side in such a way that we bisect the line PR. So PZ must equal ZR. We can draw another median by joining this corner R to the midpoint of this side PQ. So we bisect PQ into two equal parts, PX and XQ. Now, however, PR equals PQ. PZ is half of PR and PX is half of PQ. So PX must equal PZ because we're dealing with an equilateral triangle. So we can just put a single dash on PX and a single dash on XQ. So PZ equals ZR equals PX equals PQ. This is only because the triangle is equilateral. Similarly, if we draw in this median here, Y is the midpoint of QR. We get these two distances QY and YR. So these four distances are the same. Here I have shown a triangle PQR and the line or median RX drawn in. Notice that we get two triangles. Now, it turns out that these two triangles are congruent. Let's see why. Well, we've already seen that PX equals XQ, so we have two sides the same. What else is the same? Well, look at QR. I can put a double dash on QR because we know it's twice as long as QX, because this point is the midpoint of PQ, and the three sides are the same. I can put a double dash here because PQR is an equilateral triangle. So now you can see that two sides are the same in both triangles. Because PQR is an equilateral triangle, it means that the three angles are the same. So this angle here is equal to this angle here, which in turn is equal to this angle here. That's true for an equilateral triangle. The reason why is because if you say take an isosceles triangle, an isosceles triangle is a triangle that has two equal sides, then these two angles are the same. these are referred to as the base angles of an isosceles triangle. They're the angles that are opposite the equal sides. Now, if you imagine your isosceles triangle is turned into an equilateral triangle, where the three sides are the same, then these two angles are the base angles. So these two must be the same. So these are the base angles of an isosceles triangle with this side equal to this side. But this is equal to this, and this in turn is equal to this, so all three of them are equal for an equilateral triangle. Now the three angles also add up to 180 degrees, so in that case each angle must be 60 degrees. So now if we want to look at the two triangles XQR and PXR and show that they're congruent, well, you can state it like this: QX equals XP, because XR is a median. The definition of a median is that you draw a line from R to the midpoint of QP, so you get two equal lengths formed. We also have that QR equals RP, because triangle PQR is equilateral, as I've said already. And we see that this angle here, which is angle PQR, equals angle RPQ, this angle up here, because, well, again, because the triangle PQR is equilateral. Three angles are equal. So we have a side angle side situation for both of these triangles. We have two sides the same in both triangles, and the angle in between the same. So when you have two sides and an angle in between the same, we say that we have a side angle side situation. Side angle side, side angle side, which means that these two triangles are congruent. Triangle XQR is congruent to triangle PXR. So that means they're the same in every way. Everything else about them is the same. Actually, we could have shown that these two triangles are congruent in an easier way. We could have shown that the three sides are the same. So I've already stated that QX equals XP and that QR equals RP. But I could have stated that XR, that's the third side of each triangle, is the same in both. XR is the same in both, meaning it's the same in both triangles. So we have that the three sides are the same. So we have what's called a side-side-side situation. So that would show that the two triangles are congruent. We don't even have to mention the equal angles. Now, since these two triangles are congruent, it means that this angle here is actually equal to this angle here. These are corresponding angles. These angles are opposite these sides in both triangles. So PX and XQ are corresponding sides in both of these triangles because they're opposite the same angle. Well, they have the same length, so they must be opposite the same angle. So these angles have to be the same. But we know that we're in an equilateral triangle. We know that this angle here is 60 degrees, so each of these must be 30. So that means that in this triangle here, QRX, we have angles of 60 and 30. So the remaining angle must be 90 degrees. 60 and 30 is 90, 90 and 90 is 180. Similarly in this triangle. So now we've proven that this median here is actually perpendicular to this side. It doesn't have to be perpendicular. In general, the median is not perpendicular to the side. So that tells us that this median here must be a perpendicular bisector of the line PQ. So it bisects the line PQ but is also perpendicular to the line PQ. If we look at the other median of the triangle PQR, we will see that this median creates two congruent triangles. We could prove that in exactly the same way we prove that these are congruent. And because they're congruent, we can then prove that this angle must be 90 degrees. So we have a perpendicular bisector here of the side PR. In exactly the same way, if we look at the third median, bisects the line QR, we can prove that these two triangles are congruent, exactly the same way. And from that we can prove that this angle must be 90 degrees. This is 60 here, this will be 30 up here, so this one here is 90 degrees. So we have a perpendicular bisector of the line QR. So the three medians of the triangle PQR are also the three perpendicular bisectors of the three sides of the triangle PQR. It's a fact that for any triangle, the three perpendicular bisectors are concurrent, and I will prove that in another video. So here I've taken a triangle. It doesn't have to be equilateral. I'm showing the three perpendicular bisectors of the sides. So this line bisects this side, this line here bisects this side, and this line here bisects this side. And you can see that the lengths made out are not the same in general. They're only the same if the triangle is equilateral. Now the three of them will actually cross at one point, or they're concurrent to that point. And this is actually the center of a circle that can be drawn through the three corners of the triangle. So if you put your compass point here at this point and extend the compass to one of the corners, then you can draw a circle that will pass through the three corners. So this is the circumcentre. So that's the case here. The three medians of an equilateral triangle happen to be the same as the three perpendicular bisectors of the sides. So this point is the circumcentre. So if you put your compass point here and extend it to the point P, you can draw a circle around this equilateral triangle. To get the incentre of a triangle, what we do is bisect two of the angles. So let's suppose we bisect this angle here. Then we get two equal angles. We have this line here which is the bisector of that angle. And we bisect this angle here, so we get two equal angles here, which I'm calling X. And it turns out that where they cross is the incentre. If we bisect a third angle, then you will find that this line is concurrent with these two lines. Now that is something that I will prove in another video. I won't prove it here, but these three bisectors of the angles are concurrent. This point is the center of a circle that will just touch the three sides of the triangle at one point. So the three sides will be tangents to the circle. Here is a somewhat better diagram. So if you put your compass point here and extend it to just have the radius that will touch one side of this triangle, then it will touch the other side, the other two sides at one point. So the sides of this triangle are tangents to this circle. In other words, if you were to draw in this line here, you would have a radius of the circle. And because a tangent is perpendicular to a circle, or to the radius at the point of contact, we have a right angle here. Similarly here, this would be a right angle, and here. These three distances are the same. These three distances are radii of this circle. Now we showed earlier that this median here actually bisects this angle. This angle here is 30 degrees. This is 30. Similarly, by exactly the same reasoning, we can show that this median here bisects this angle. This median here actually creates two congruent triangles. This triangle up here and this triangle down here. They're two congruent triangles, so it turns out these two angles are equal angles. Just exact same reasoning as before, just applied to this triangle here and this triangle down here. And similarly, we can show that this triangle here is congruent to this triangle here, which means that these two angles are the same because they're both opposite pair of corresponding sides. So you can see now that this median here bisects this angle, but this median here bisects this angle here. But the intersections of the bisectors of two angles of a triangle is the incentre of that triangle. So this point is not only a circumcentre, it's also the incentre. So in other words, this is the centre of a circle that just touches the three sides of this triangle. So for an equilateral triangle, this point here is the centroid, the circumcentre, and the incentre. In part 3, we want to prove that this point, which is called G by the way, is the orthocentre of the triangle. Now what is the orthocentre of a triangle? Well, here is a triangle, and I've drawn in two of the altitudes or heights of this triangle. So here we have the intersection of two of the altitudes. That point is the orthocentre. So you just draw a line from one of the corners perpendicular to the opposite side. It turns out, by the way, that these the three altitudes are concurrent at this point. Again, that is not obvious, and I will prove it in another video. So, how do we prove that this point here is the orthocentre of the triangle? Well, if we look at these medians, we see that they're actually perpendicular to the opposite side. So these three medians are actually altitudes for this triangle. And the three altitudes, as I've said already, intersect at a point called the orthocentre. So this point is also the orthocentre.